Hello again, and welcome back to our journey into system design. Today, we're diving into a core component of any large scale system: database design. Whether we're creating a small application or a complex distributed system, the database is the backbone of how data is stored, accessed, and managed. Let's think about this. Every time we send a message, make a payment, or even just browse content online, databases are working behind the scenes to store and retrieve information. They ensure that data is available when we need it and that it's accurate. But here's the catch. As our system grows, more users, more data, and more traffic will put pressure on the database. If it's not well designed, the system might slow down or even crash under that load. So today, we'll focus on how to design a database that supports our system's scalability and reliability while maintaining efficient performance. This is the foundation for ensuring the system can grow with our user base while staying robust and secure. Ready? Let's jump in. Now that we've explored the concept of a simple application, let's dive into distributed systems. A distributed system is a model where components located on networked computers communicate and coordinate their actions by passing messages. This architecture enables flexibility and scalability, as resources can be added or removed as needed. Distributed systems come into play when we want to handle increased loads, enhance fault tolerance, or provide services across different locations. Think of services like Google Drive or Dropbox, which allow users to access their files from anywhere. The magic of distributed systems lies in their ability to work seamlessly together, even when they are physically separated. In a distributed system, multiple nodes or servers collaborate to process requests. When a user uploads a file to Dropbox, for example, that file is distributed across multiple servers, ensuring that if one server fails, others can take over, providing reliability and accessibility. So, as we move forward, let's understand how these systems work and the key components that make them effective. To understand distributed systems better, let's look at their key components. First, we have nodes. These are the individual computers or servers that work together to form the system. Nodes can be physical machines or virtual instances, and each one plays a crucial role in the overall functionality of the distributed system. Next, we have communication. This is how the nodes exchange information with one another. Effective communication is vital for the nodes to synchronize their operations and ensure they are working together efficiently. Then we have data storage. Distributed systems require a way to store data across multiple nodes. This means that data isn't just kept on one machine, it's spread out across several nodes to ensure availability and redundancy. Another important component is load balancing. This ensures that no single node gets overwhelmed with requests. A load balancer distributes incoming network traffic across multiple nodes to prevent any one node from becoming a bottleneck. Next is fault tolerance. This means the system can continue operating even if one or more nodes fail. Fault tolerance is essential for maintaining reliability and availability, ensuring that users can access services without interruption. Lastly, we have scalability. This allows the system to grow by adding more nodes as demand increases. Scalability is crucial for adapting to changing loads and ensuring the system can handle more users over time. These components work together to ensure that distributed systems can handle various tasks effectively. By understanding these components, we can appreciate how distributed systems operate efficiently and reliably. Now that we understand the key components of distributed systems, let's explore their benefits. First and foremost, increased availability. Distributed systems enhance the availability of services. If one node fails, other nodes can continue to provide service, ensuring that the system remains operational and responsive. Next, we have improved performance. By distributing the workload across multiple nodes, distributed systems can process requests faster as tasks can be handled simultaneously. This parallel processing is crucial for applications that require quick responses. Then comes scalability. As demand grows, distributed systems can easily scale by adding more nodes to accommodate increased traffic. This flexibility allows businesses to adapt to changing user demands without significant rework. Another important benefit is cost efficiency. Distributed systems can leverage inexpensive, commodity hardware, instead of relying on expensive, high-end servers. This cost-saving approach makes it easier for organizations to manage their resources effectively. Lastly, we have fault tolerance. As we mentioned before, distributed systems are designed to withstand failures. By having multiple nodes, the system can continue functioning even if some components fail, which is vital for maintaining user trust and reliability. In summary, the benefits of distributed systems are clear: increased availability, improved performance, scalability, cost efficiency, and fault tolerance. Understanding these benefits helps us appreciate why organizations are moving towards distributed architectures for their applications. Now let's dive deeper into understanding how distributed systems actually work. At the heart of a distributed system is a group of independent computers, or nodes, that work together to perform a task. Each node can perform different tasks, but they communicate through a network to achieve a common goal. Distributed systems follow a client-server model. The clients send requests to the server, and the server processes those requests. However, in a distributed system, there can be multiple servers working together, distributing the load efficiently. One of the key aspects of how distributed systems work is data replication. To ensure high availability, data is copied across different nodes. This way, if one node goes down, another can take over, providing uninterrupted service. Next, we have load balancing. To prevent any single server from being overwhelmed with requests, the system uses load balancers. These balancers distribute incoming traffic across multiple servers, ensuring smooth and efficient operation. Lastly, distributed systems utilize message passing. The different nodes communicate with each other using messages over the network. This message passing mechanism is essential for synchronization and coordination between the nodes, ensuring they work harmoniously. In short, distributed systems work through a combination of nodes, client-server models, data replication, load balancing, and message passing. Each of these components plays a vital role in ensuring that the system functions efficiently and reliably. Now that we understand the key principles of system design, let's dive into the primary components that make up a system. At the core of every system, we have a combination of the front end and back end. The front end is what users interact with directly. It's the user interface. The back end, on the other hand, handles all the behind-the-scenes processes, such as storing data, managing business logic, and communicating with databases. Next, we have the database. It's where all the essential information and user data is stored. But as systems grow, a single database isn't always enough. We also need to consider caching to speed up data retrieval and load balancers to efficiently distribute traffic across multiple servers. All these components must work together seamlessly to ensure a smooth and responsive experience for users. Let's now break down the difference between the front end and back end in more detail. The front end is what users see and interact with. It's the graphical user interface, often developed with technologies like HTML, CSS, and JavaScript. This is where users can enter data, click buttons, and navigate through the application. On the other hand, the back end operates behind the scenes. It handles the logic, database interactions, and server-side operations using languages like Python, Java, or Node.js. When a user submits a form, for example, the back end processes the information, stores it in the database, and then returns a response to the front end, ensuring everything runs smoothly. Now that we've covered these key principles, you should have a solid understanding of the foundations of system design. Remember, applying these principles is what makes modern applications scalable, reliable, and efficient. And these are the exact techniques that companies like Netflix, Uber, and Instagram use to deliver smooth experiences to millions of users. Thank you for being part of this journey today. If you found this session helpful, don't forget to hit the like button, share this video, and subscribe to stay updated on the latest content. There's so much more to come, and we'll be diving deeper into system design in our upcoming sessions. Stay tuned.